Okay, thank you very much. I'm Nobuyasu Ito, actually the organizing chair of this symposium. So today I will talk about my team collaboration against COVID-19 diseases. So main title is about the economics, and Professor Inoue, he will just succeed my short presentation about the detail of that. Anyway, using the Fugaku supercomputer since last April, we R-CCS collaborating with many Japanese and international collaboration to attack the COVID-19. So Tsubokura Sensei's talk, previous one is that one of that, and Sugita Sensei were the invited talks for Tanaka Sensei's project, and those are the one of the 6 teams. So here is only 5, maybe one is missing, but anyway. So we, my team is doing some social aspect of the COVID-19 disease and spread. And okay, so this is a collaboration with many Japanese universities together with RIKEN, and also financial and supercomputer support from the Japanese government. And that the collaboration include the infection spreading simulation and macroeconomics, and also cooperation activities simulation, and also social sentiment analysis using the social media text. And now this is one example. So I make up a agent-based model for the COVID-19 disease spread for the Fugaku supercomputer. And here's the example that how the so-called the infection cluster formed or collapsed. And this is a typical behavior. And here's some size of the infection cluster start to appear around the so-called the basic reproduction number R naught around 0.6 and above. If the R naught becomes larger than this number, it's quite obvious, socially obvious, that the COVID-19 start to spread in the society. And then if we introduce the so-called the contact trace application in Japan, we are now preparing and operating the so-called the COCOA application with the Japanese government. And that has some power to reduce the infection peak height for the infection cluster. And here is some complicated plot, but anyway, without for every basic reproduction number, the size of the infection cluster is reduced from the no contact tracing cases with some contact tracing with a very shorter alert times. And roughly speaking, we have the contact trace application of the power to reduce the reproduction number about 0.0 to 0.3. That's quite effective to suppress the COVID-19. Okay, some more things we are doing some GPS analysis to see how the Japanese people are moving or active in our area. So this is a GPS mobility analysis using the Fugaku. That 1 month mobility data for the November last year, and also some text mining how the human sentiment is changing with time. Anyway, those are the many things, but today I would like to concentrate on the economic simulation, and I will introduce Professor Hiroyasu Inoue. He is actually the guest researcher in my team, and he is a professor, associate professor in the Kobe, Hyogo University. And he got PhD from Kyoto University, and then he was a visiting professor also at the Center of Complex Network Research at Northeastern University and Kiel University. So his research interest lies in complex systems and computational social science. His recent paper was published in Nature Sustainability. Okay, Inoue Sensei, are you ready to go?
I'm ready.
Okay, please.
Yes. Thank you for the introduction. I'd like to start my talk. I'm Hiroyasu Inoue from University of Hyogo. My talk is about economy, as Ito Sensei said. And as we know, most countries have imposed lockdown or restrictions to their own countries. And the economic impact is enormous, basically. And the estimation of that is, of course, important. However, it is not easy because the economies, basically, they are connected and the spillover can happen. So even if some region, only one region is restricted or locked down, other regions will be affected because they are connected. And so, moreover, lockdowns, now we have many lockdowns, but they are not coordinated in the sense of timing. Like Sweden last year did not impose a strict lockdown, but the benefit of that in the sense of economy was very limited. Now Japan has imposed second restrictions this year. However, first 4 prefectures, the restrictions were imposed to those 4 prefectures first, and after that 6 or 7 prefectures added. So what if we impose lockdown or restrictions to those prefectures simultaneously? There is maybe some difference in the sense of economy. So the purpose here is to use a large-scale supply chain data. It covers almost all Japanese firms. I will explain this later. And we built a simulator and to investigate the impact of those restrictions. And however, of course, there are conventional economic models, like one is IO table or general equilibrium model. However, they are not sufficient because IO table is a aggregated data. It's like industrial sector data, and they it's a technical thing, but it can be applied to demand side shock, but the supply cannot be considered. And the general equilibrium model, they have strong assumption, like all firms are homogeneous, but in reality, in the sense of, for example, supply chain data, every firm has different trade partners. So if we introduce such things, these economic models cannot be used. So for this kind of estimation, unfortunately, this methodology cannot be applied. So first, I'd like to explain the data itself. This figure shows a supply chain data of Japan. It covers 1.6 million firms and 6 million trade partners. In this figure, each dot shows a firm and the color shows a sector. And the size of the dot shows a number of partners. If they are located, they have connections of trade partner, they are located closely. But links are not shown because if we draw that, we cannot say anything. So yeah, there are over 1.6 million firms here. So we run simulation to replicate the economic dynamics or reactions in Japan. So we need some model on, because it's just a map of a supply chain here. So we need to run something. So there are possible numerous models here, but what we have thought was like to simplify model so that we can replicate the short-term economic reaction. So this model is quite simple. There are 4 processes every day for every firm: order, demand, production, inventory, renewal. So there is no market or price mechanism. So if we consider that, we can use this model for short-term prediction or replication. And I will explain this. I cannot explain the detail, but the first one is order. Order is decided based on the demand, 1 step before one previous day, and the adjustment of inventory. In this model, the inventory is considered for supplier's product, so like input for production. And to adjust that, there is a order volume here. And the summation of order from the downstream firm is, and the final consumption's demand is the demand for this firm. So considering this demand for this form and the input inventory, of course, this is a constraint to produce. And the last one is capacity. Since this is under some negative shock, this form may be directly affected, like disaster, or in this case, COVID-19's restriction, like the scarcity of labor. So the capacity is normally equal to the pre or negative shock level or initial level, but in that case, directly affected, capacity is lower than that level. So considering these three terms, the actual production level is decided, and based on the production, from suppliers to client, that production is delivered to downstream firm, and the inventory is reviewed. Previous days inventory and the order, it's a realized order. So not all order is realized because it's under negative shock, and minus consumption to produce. That's it. Very simple model. And the scheme of this, of this simulation, some firms are directly affected, and the supply cannot be delivered enough to downstream firms. So therefore, these clients also have to decrease their production, and the same thing happened to the downstream firms. And in the demand side, is the same thing. This firm cannot demand enough, like it's lower than before. So the upstream firm has to decrease their production, and the same thing happened to the upstream firms. So it's kind of propagation or penetration happens in this model. Then we apply this model to a real earthquake data first. So we get the earthquake and tsunami shock from the real data, and we apply that to our model. But we have, of course, so many unknown parameters, so we searched that by using HPC. In this figure shows, in this figure, horizontal axis shows a day, and the vertical axis shows a daily value added or GDP. So the pink dot is a real economic reaction. So so that we can replicate these dots, we've tried to find parameters. And this is a simulation. So first, the east part has negative shock, and surprisingly, in a few days, the shock is propagated to other areas. Why this happened? Because there are so many reasons, but one reason, strong reason, is network structure, supply chain structure. This in this figure, the number of links of each dot and the probability, but it's complementary cumulative probability or rank size plot is shown here. So we can see it's a log plot, and fat tail distribution is not a exponential decay. So means there are so large hub in this network. If there is such a huge hub here, the average path length between arbitrary nodes is log n, and is a number of nodes or farms here. So now we have 1.6 million farms, but the actual number of this average path length is only 4.8. So it's very, how can I say, it's any farms are indirectly connected in a short path. So because of that, that propagation is quite fast. Now we go back to a COVID-19. This is the actual restriction case in last year, April and May, and we again calibrated our model. And this is a temporal and visualization, but this time it's corpus. In the beginning, the metropolitan or highly populated area were under restriction. However, that as we can see, the propagation again quickly propagated to other areas. However, that shock is relatively mild compared with the earthquake case, because the color is not so strong, as we can see, because it's compared with a earthquake. Earthquake is a kind of devastating, so they cannot substitute the input or products. But in this case, this restriction is not that strong, so the farms can, complement each other. So because of that, this shock is it looks very mild. And now 2021 from January 8th, we have another second restriction. So by using our simulator, we can estimate the loss. This is loss estimation. So in schedule, it's 2 months, but we can calculate like what if we extend the restriction 1 to 4 weeks. And importantly, the daily loss increases because of the penetration to other areas. And this is a vertical simulation, like what if we, impose restriction to Tokyo, the propagation and affected areas, so many, but we can only see such phenomena in Tokyo. In other cases, it's very limited. So in Japanese economy, Tokyo is a kind of dominant area. And this is another vertical two prefectures restrictions with Tokyo and another prefecture under restriction. What happened? An interesting result is like Kanagawa is has the second largest GRP. The top is Tokyo, and Osaka is the third. Even so, if we if Tokyo and Osaka simultaneously restricted, the GRP loss, GDP loss is greater than Kanagawa, because this is because Osaka has some different function in a sense of economy, in economy. So I think that is a kind of a hypothesis. Anyway, because of the time, I will skip another slide. And anyway, I could not share a lot of other findings we have, but this is a take-home message. It's just we, based on the supply chain data, we built a nationwide simulator to predict or replicate a short-term reaction of economic negative shock. That's it. Thank you.